All right, we've still got a few folks joining, but we'll go ahead and get started with the webinar. Welcome, everybody, and thank you for joining us. My name is Josh Seimer. I'm AFL's Market Manager for Service Providers. I'm here to talk about network convergence for everyone. So, first, a brief introduction for those of you who are not familiar with AFL. We are a global leader in fiber optic products, conductor accessories, and services. We're based in North America. We're a fully owned subsidiary of Fujikura, so we have a larger organization around us supporting us with additional technology. But we are ourselves a global entity with 11 global manufacturing locations, core values of community engagement, innovation, environmental health and safety, integrity, customers first, and collaboration and accountability. And our mission is to connect our customers around the world with innovative technologies, exceptional products, and high quality services. What we'll be talking about today is, first of all, why network convergence and why is this important for all network operators? The term network convergence has been around for a while, several years, but to a large degree, it's been used by larger network operators in their operations. But with newer technologies and newer applications and the current trends in our markets, network convergence is becoming important for all network operators, and we'll talk about why that is. Then we'll talk about what a converged network is. We'll talk about key characteristics for a converged network that gets built today. Those key characteristics being expandability, flexibility, and accessibility. And then finally, after talking about the why and the what, we'll talk about the how. So how do network operators build a converged network with these three characteristics? For questions, we have a questions feature on this software that we use, GoToWebinar. You should see it on a little control panel. Please use that to ask questions, and I will address those questions at the end of the presentation. So first, we'll talk about why a converged network. And the quick answer is because there are so many different usage cases and applications now generating so many different types of traffic that a network needs to be designed, especially an access network needs to be designed to accommodate all of them simultaneously using the same physical infrastructure. Usage cases. If we look at just 5G, which is just one of several trends affecting the construction of networks and their operation, well, with 5G, there are three main usage cases. Enhanced mobile broadband, meaning delivering more bandwidth to devices that are mobile. Massive machine type communications, which is enabling machine-to-machine connectivity in numbers much larger than we've ever had before. So with not necessarily a person being in the loop there. And then finally, ultra reliable and low latency communications, enabling that quick response for the network. And with each of those, $5G alone generates the potential with those three usage cases for a substantial number of different applications and specific devices which use those usage cases. So this trend alone is generating a lot of different types of traffic as well as volume of traffic onto networks. And with the rapid pace of applications and usage cases for digital technology as a whole, you can see that this is just a subset of 5G applications, and 5G applications being just a subset of all digital applications that will drive different types of traffic onto the network. You get an idea of the diversity of things, of traffic that exists not only today, but could exist and will exist years into the future. Along with that, now you have a growth in both the number and in the variety of devices that are connected. So you've got more applications going, but you're also connecting to more different things at the far end of the network. In terms of numbers, you can see in this graph on the left, projecting to go from 15 billion connected devices worldwide in 2015 to 5 times that number in 2025, and continued growth at that rate well into the future. So there's a variety of connected devices, examples, 3D printers, smart refrigerators, smart watches, traffic lights, smart kiosks, sensors, and even agricultural equipment in rural areas now is highly connected and has a great deal of automation. And that means a variety of endpoints for a fiber network. The endpoints of a fiber network, well, we often talk about fiber to the home. Yes, a home is still going to be an endpoint for a fiber network. Fiber to the business, fiber to the business. Yes, businesses will still continue to be endpoints, but as this example gives you a sense of the number of devices within those businesses that represent unique endpoints will continue to grow. And here you see a highly automated factory with a large amount of manufacturing equipment, each of which represents a distinct endpoint for a network. And whether it's connected wirelessly or directly to a fiber or copper connection, each of these equipment items generates traffic, and it does go on to fiber in most cases before it even leaves this building. We see the proliferation of small cells. So cell sites that cover a smaller area in order to provide greater bandwidth and lower latency to subscribers in that area, as well as fixed wireless connections being used. Macro and larger cells, more and more connections going there. So macro cells, you might see more radios going out. Data centers, we see a trend to edge computing, meaning pushing data centers out closer to the end users, which means more smaller data centers versus the trend from the previous decade, which was more centralization into cloud data centers. And each of those data centers represents an endpoint for a fiber network. And of course, the traffic light example, each of those traffic lights now, each intersection and potentially each individual light now is an endpoint to the fiber network. And we have this continued trend with mobile wireless towards cell site densification, which increases the number of endpoints to a fiber network. To deliver more bandwidth and lower latency, areas that used to be covered by a single macro cell now get covered by 4 or more. In these examples, you see the same coverage area getting divided now into 4 and then 16 small cells. Well, that's 16 times as many endpoints for the fiber network. So all of these cases are generating different types of traffic, different usage cases, and for the network operator, revenue opportunities. So that brings us to the question then, what is a converged access network? The converged access network is a single physical infrastructure that is designed to support these different usage cases and traffic types. What you see here is a very simple example with 4 basic traffic types. We've indicated with the colors 5G front haul, so connecting a 5G hub to small cells. The backhaul, which connects a macro site, in this example, a macro site and a CRAN hub, back to a central office head end switching center or other centralized location. You have FTTH, which in this example, we're showing using a passive optical network. So that's shown out here, going through a splitter cabinet and then out to individual homes. And in this case, point-to-point business type services, which we are showing going to an enterprise location and then to another campus and venue location. And each of these combines at different points into the same physical infrastructure. So in this area, you have a single cable that, again, in this very simplified example, is handling 3 types of traffic, 3 types of traffic here. But in practice, there are many more usage cases, types of traffic that exist. And so it's not practical to design a different and build different networks to handle each of these types of traffic. You have to combine them into a single physical infrastructure to make the most ROI on your investment in that physical infrastructure. And while this example with the icons you see here shows a more urban and denser suburban setting, the use of the converged access network is not limited to that setting. Just to give you a few examples, in an urban area, these small cells might be close together. In a less urban area, they might be farther apart, but the general trend of densification occurs in small towns just as well as in larger ones. In the FTTH network, these homes could be close together. They could be farther apart. The campus and venue could be a stadium in a large city. It could be a rural college campus, such as this one, which is a few miles away from my house. The enterprise could be a large office complex like you see here, or it could be shops in a small town, because as the demand for connectivity grows, you'll see that each of these will become more and more demanding of bandwidth. Each of these will become an endpoint for a fiber network and will drive different types of traffic onto that network. This creates some future opportunities and also challenges for network operators. The opportunities come when these new usage cases and these new applications generate demand for what the network operator is providing for that infrastructure. The challenges come in making sure that the infrastructure can handle and accommodate that demand in a responsive way. So here are just 3 examples out of many. We could come up with dozens and dozens of these. 3 examples of future opportunities and challenges for network operators. One is something we've talked about already, which is that wireless densification. And so in this scenario, a service provider is operating a fiber network, and 1 or more mobile providers add multiple small cell sites to cover an area that previously had just 1 macro site. And again, this is not strictly an urban and suburban phenomena, though it occurs there most dramatically. This is occurring in small towns as well. Again, not far from my house, Camp Ripley, Minnesota is located in a rural area. There's about 1,000 people who work there full time. And there are small cells now being deployed in that area to ensure that those 1,000 people who work in that area have adequate bandwidth. And again, it's Verizon and T-Mobile putting those small cells there. So it's a rural area, but large mobile operators are coming in and densifying their network there. And so the business opportunity is those mobile providers are willing to pay for fiber capacity to save the cost of deploying their own network. It is expensive to run your own fiber out just to a small cell site. And if there's an existing fiber network, it's usually more economical to lease space on that. So as a network operator, you can drive that as revenue. But the challenges are that fiber network operator must have enough capacity that they can expand to provide this service, have the flexibility to accommodate connections where the mobile operator wants them, because they're going to decide where to put those small cells based on the radio frequency coverage that they want, not off of the fiber network that's previously existing. They'll be able to make some adjustments, but they're limited in the adjustments that they can make location-wise to get the coverage that they want to achieve. And then the third challenge is technicians must be able to actually access the network, go out and physically make these changes to connect these customers. Business automation presents another scenario. And in this specific scenario, let's imagine that in a small town, a car repair shop closes and a 3D printing shop moves into the same location. This is something that's also happened near me. Well, there's an opportunity for greatly increased revenue for providing more bandwidth and services. If that custom 3D printing shop is being a contract manufacturer for a number of small firms in the area, there's going to be a lot of traffic going to and from those 3D printing devices, much more than the car repair shop would have been using. So that's an opportunity for increased revenue. But the challenge is ensure network capacity can expand to provide this service, having the flexibility to accommodate connections where this new customer exists, and technicians must be able to access the network to make those changes. And finally, a fairly common one around small towns and on the edges of metropolitan areas especially is subdivision. A property is subdivided to build multiple homes and businesses. Well, the business opportunity there is where once there was one potential customer, now there are many. But it can be very expensive to serve those customers if the network doesn't have the capacity and can't expand to serve them, or if it doesn't have the flexibility to accommodate those connections where these new customers exist, or if the technicians can't physically make those changes to the network when and where they're wanted. So you can see some pretty consistent themes here. In each case, the challenges have to do with expandability, flexibility, and accessibility of that converged access network. And that's why we call those the key characteristics of this converged access network. So again, expandable, meaning the converged access network must have the capacity to accommodate future growth in traffic, new business and usage cases, and more. So the ability to deliver aggregate bandwidth, as well as the ability to separate out that traffic as necessary based on the protocols being used, NG-PON, GPON, various point-to-point protocols, etc. It needs to be flexible, meaning you have to have the capability to reconfigure it to accommodate moves, adds, and changes, or new technologies. For example, we've talked about the changes that 5G is going to bring. We can't even imagine what changes 6G will bring. That's 9 or 10 years in the future. But if you're investing in building or upgrading a fiber network today, you need to be thinking about how well it's going to handle 6G, because you'll want that network to last a lot more than 10 years. There'll be new business cases and revenue opportunities for that network operator. And again, all the other events we can't specifically plan for now. Again, 6G being just one example. We don't really have any clear idea what that will do to the fiber network, other than it'll require it to change and it will drive more aggregate bandwidth onto it. And finally, you want that network to be accessible. So it's one thing if you have the design capability to say, oh, sure, we'll add a connection here. If it is a time-consuming, risky proposition to send someone out to actually make that change in the network, that's not a good thing either. Your technicians and contractors need to be able to readily implement those network changes quickly and in a cost-effective way, so that you can serve these customers before they find an alternative means of getting the bandwidth they're going to require. So that leads us to the question of how. Okay, how do we build a converged access network that has those key characteristics? Now, I could write a book about this, and I could talk about it for days. We're not going to spend days on this webinar. But I'll give you a few examples of some ways that you can think of adding expandability, flexibility, and accessibility to your concept for a physical network. So first, let's talk about expandability. The easiest way to think about expandability is by having more fiber capacity. So more fiber means you can have that fiber available to use for whatever service is required to put on it in the future. Now, the challenge becomes capital expenditure, because if the business case for using that fiber is unclear today. Again, we've got an idea that in the future there's going to be more bandwidth demand, but we don't always know exactly when and where. It can be difficult to justify that capital expenditure. But fortunately, deploying more fiber today does not drive up the costs of network construction proportionally. And some of the products that enable this are newer, more compact cables, such as AFL's wrapping tube cable and the air blowable variant of the wrapping tube cable, which they're more compact. That allows you to provide more fiber in the same size ducts. So you don't increase your expenses for the duct itself. You don't have to make a bigger trench or a bigger borehole to run that duct through. And yet you can deploy more fiber in. And you can see examples over here of how AFL enables deployment of up to 432 fibers in duct space that's significantly less than competitors can deploy 288. In an aerial deployment, weight is an important factor, and these newer compact cables can provide more fiber for the same amount of weight. And finally, smaller cable means you can fit more, and a lower weight per length means you can fit more on a reel, and that means less splicing to reach the same distance. So that makes it more cost effective over longer distance runs to run more fiber because you're not driving up your splicing costs. Again, the longer length and fewer splice points balances increasing the fiber count. So the end result of all of this is in an access network, you can deploy twice the fiber for a tiny increase in the total cost of deployments, less than 10%, in some cases as little as 2%. When you consider all of the labor costs and all of the other materials that go into the network, you can design in twice the fiber for substantially less than 10% additional cost. And that becomes a more valid proposition at the beginning to say it's a comparatively small CapEx increase to get this capability in the future and hopefully obviate the need to come back and push more fiber through and incur all those labor costs yet again. Here's another way of providing expandability in the network. Again, goes back to making more use of existing space as well as the existing financial resources. And with this, you've got new compact splice closures, such as the AFL Apex closure, give you more splicing in the same or smaller handholds, more splices for less weight and space on the pole or strand, while still leaving plenty of room for future additions. And this is important because it saves you not just the cost of purchasing and installing a larger handhole compared to a smaller one. It also gives you more flexibility in where you can locate those handholes. It's simply easier to find a spot to put a 17 by 30 handhole in this example compared to a 30 by 60. And here we're showing 864 fiber splices. On the left, you can see currently, in a lot of cases, that takes a 60 by 30 handhole. Newer products allow you can do that potentially in as small as a 17 by 30 handhole, and that's been demonstrated and proved out. So we can deploy up to twice the fiber today, leaving room for additions for little to no additional cost, and in some cases, even reduced cost. Give yourself more capacity and still use a smaller handhole. So the sum total of that is, these are just two examples of how product design can allow for network operators to build an expandable network today that gives you twice the capacity, twice the capability to accommodate future demands at little to no increase in the cost of deploying that network. Now let's talk about flexibility. So you have the aggregate capacity, but like we talked about earlier, When you start looking 10 years or more in the future, it's hard to predict where and how much those new demands on the network will be. So some examples, so you need the flexibility to come in where those customers pop up, where those revenues opportunities occur. You can do that with things like modular fiber panels, which allow you to change the types of connectivity, SC, LC, MPO, have more fibers, more traffic running through that to accommodate traffic growth. So single fiber connections today, MPO connections in the future, put in other types of modules to run more wavelengths over the same fibers. All of those things are feasible. And if you have a modular fiber panel, such as AFL's Ascend fiber panel shown here, you can accommodate that readily. Splice closures that are modular and compact, such as AFL's Apex, which has the same splice tray for ribbon or single fusion, which means you can carry fewer SKUs around in inventory, and your technicians can carry fewer around, and you can easily adapt that. But also that compact size allows you to have more current and future connections in the same space, and even less space in some cases. So that means, again, similar upfront investment. You now have the flexibility to come in and say, wow, now there's a subdivision here. I need to run a new cable back to this splice closure. You have room to do that without having to oversize that handhole as much as if you were using an older generation, larger splice closure. And finally, plug and play solutions, such as the Titan and AFL's Titan and Trident system here, allow you to readily add new connections without having to deploy a splicer, prep, splice, and pack up. So you can deploy a 12-port terminal. If it's an area where currently there's only demand for 4 of those ports, you have 8 more ports available, and all it takes to make use of them is going out there with a drop cable and making a connection. Again, no need to deploy a splicer, prep, splice, and pack up, which has a significant investment in time. Okay, so, and that relates then to the question of accessibility. So it's one thing if, from a design and theoretical standpoint, you can say, okay, I have this flexibility point in my network, I have this splice closure, I have this cable running through it that has enough capacity to handle this new customer. Someone's got to actually go out and make that happen. And again, it's hard to predict what that will be. Maybe in the future, there'll be an additional demand for 12 or 24 fibers to connect at a certain splice closure. Maybe it'll be 3. Fortunately, new fiber ribbon designs, such as AFL's spiderweb ribbon, allow for the speed and efficiency of mass fusion splicing for large counts, but also allow for easily breaking out smaller counts when and where needed. So if you have to come out and make a connection for 3 fibers, it can be done readily in that ribbon cable. If it's 12 or a multiple of 12, you can use it as a ribbon. And also, it's important to think about dissimilar fiber types going out in the network. As 200 micron coated cable or coated fiber becomes more common, you're going to have more junctions between 200 micron and 250 in that network going into the future. And fortunately, there are ribbon designs which make that a much more straightforward proposition. By putting that 200 micron fiber in a ribbon at a 250 micron pitch, you can avoid the need for special tools, special V-grooves to adapt one to the other, reduce the time it takes to make those connections, and make that a much more straightforward process, again, while still getting the benefits of doing mass fusion instead of single fusion splicing where that's practical. Some other considerations for accessibility. Splice closures. Any splice closure you get today is going to be re-enterable. But the question is, how practical is it to re-enter? It has a capability, but the more difficult it is, the more likely it is that you're going to have an error. And that leads to how easy is it to reseal correctly. So if it's re-enterable, that means that has the capability to be resealed. And again, any splice closure today is going to have that capability, but look closely at what it takes for the technician to make that reseal correctly so that it keeps liquids out, because of course an error there could lead to some pretty disastrous consequences down the road. And then can that closure with enough cable slack fit in a given size handhole, strand, or pull space? Real estate is important. Real estate can be expensive, even in rural areas. If you're talking about space on a strand or space between one communications provider and the electrical space, all of those, space is money too. And again, if you can see, as in this diagram on the right, you can fit more fiber plus enough slack to work with, cable slack to work with in the future in a given size or a smaller size space. That gives you a lot more options and can save you a considerable amount of money. Plug and play solutions, we talked about how they're flexible. They're also very accessible. Make network changes without splicers or special tools and turn up customers a lot sooner. And examples include hardened terminals with connectors, as well as those modular fiber panels again. And then finally, splicing, testing, and inspecting. Simpler to use equipment is important so that you can get technicians out on the scene doing this work with fewer errors and less time spent training and learning the equipment, and making it easier to record and store data to simplify tasks and reduce errors. So the better documentation you have of your network, the better you're able to go out and make changes to it in the future, because you know where things are, you know what they tested to, you know that they were tested, you know they were working at a certain point in time, but only if you're able to record and store that data. And so having equipment that makes that task easy is critical to the accessibility question, and in turn to the network operator's ability to gain these business opportunities in a timely manner. So in conclusion, all network operators, not just the big ones, not just the urban ones, should plan for and build converged access networks to ensure that they can capture current, emerging, and most critically, unforeseen business opportunities. But to be able to do that and capture those business opportunities, converged access networks must be expandable, providing the capacity for future needs, flexible, meaning you can redesign them to accommodate those needs when and where they occur, and finally accessible for someone to actually make those accommodations for those customers and revenue opportunities. And finally, new developments in fiber cable and connectivity products make it easier than ever to build a network with these characteristics. And with that, we'll roll into the Q&A. I will open up the questions window here, and feel free to type a question out if you have one, and I will address them as they come in. I'll pause a minute to give folks a chance to type. Okay, I've seen no questions come in so far, so I will stay on here for another few minutes just in case someone is still typing. But for everyone else, thank you very much for attending this session. My email is there on the screen. Everyone who registered, whether you attended or not, will get a link to a recording of this webinar, so you can rewatch it, and you'll be able to see my email up there again if you're not able to record that at this precise moment. So you'll have another chance to see it. But I look forward to receiving any additional questions over email if you have time to think about it, and I look forward to helping everybody understand more about the Converged Access Network and why it is for everyone. Thank you. Okay. One question I do see we've got in is, what is the cost of AFL new ribbon cable? That came from Hassan. And Hassan, what I will do is I will get, we have your contact information from the registration, and I will make sure we have someone get in contact you to talk about that. Obviously with different fiber counts, jacket types, etc. There's, armored, non-armored, 144 up to 1728 cable. There's no quick answer to that question, so I will have someone get in touch with you to answer that. Thank you for the question. Okay, once again, thanks everybody, and take care.